My name is Isaac Hayward, and this is my digital sampling lab. The main motivations of this lab were to gain experience on digital data acquisition systems, to analyze sinusoidal waves from digital data, and to also explore the relations between power spectra and different time histories. This table represents our waveform identification data taken from our system. The more notable signals that we'll talk about are track 7 and 8, where they were both sine waves with noise. However, track 8 was a sine wave with more noise than track 7. And also, with our track 11, which is our sine wave of a sine wave, we didn't have a single peak frequency as the frequency constantly was shifting. Now let's move on to my personal experiment. The motivation for my experiment was to test the accuracy of my guitar tuner. And by carrying this experiment out, I found out it would actually help me play better and help boost my confidence, as I knew that I would have equipment that actually works and is actually helping me. And with that experimental motivation in mind, I explored many questions with this experiment. One question being how close my perfectly tuned strings were to expected and already established tones. So what I mean by that is I would tune my guitar to the quote unquote perfect spec with my tuner. And, I would record those tones into our DAC system, and I'll see what frequencies show up, and I'll compare those values to expected frequencies that I should be hearing. And another question that I had that I wanted to explore was the accuracy of my strings. So, once I did compare the frequencies of my strings with expected values, I wanted to see how far they deviated and what was the average among my strings. The main goals for my experiment was to successfully record frequencies of each of my guitar strings, to also obtain expected frequency values for each of the strings, to compare those values, and to also conduct analysis based on what I found. To carry out my experiment, I first tuned my guitar with the tuner to its quote-unquote perfect spec. I then set up a mic and data acquisition system with my laptop, shown on the right. After I ensured that my guitar was tuned and that my data acquisition software was working, I played a chosen note one time into the microphone, where I could then record peak frequencies that would show up in the system. And I repeated this process for each of the 6 strings on my guitar. And once I got the frequency values for each string, I then compared the values using the equation below, where the measured value would be the frequency values that I got from my data acquisition software, and the expected values would be frequency values of my guitar that I researched online for. And with that equation, if I saw that the value that I got was bigger than 0, then that would note that my guitar string was actually sharp or higher than it should be. And if the value of X was below 0, it would note that my guitar string was actually flat or below what it should be. Here's the data I collected from my experiment. On the low E string, I found that the measured frequency was 4.28% higher than it should actually be. For our A string, I found that the measured frequency is 2.34% lower than it should have been. For our D string, I found that the measured frequency was 2.42% higher than it should have been. For the G string, I found that the biggest difference actually, I found that the measured frequency was 12.31% lower than it should have been. For our B string, I found the measured frequency to be 4.3% lower than it should have been, while our high E string was found to be 2.23% lower than it should have been. And what I mean by lower, I meant that the string was actually flat, while if I said higher, I meant that the string was sharp. For this experiment, I had 2 success criteria I needed to meet. One criteria being I needed the average string frequency difference in my measured values of frequency versus the expected values of frequency. I needed that average to be less than 5%, in which it actually was, where I found my calculated average to be 4.65%. So I did meet this criteria. However, I was not able to successfully satisfy my other criteria, which was that I needed the frequency of my strings to not deviate from either plus 5% or minus 5%. And the string that broke that rule was our G string, where there was a 12% difference, which is way above my limit of 5%. And with all this in mind, I concluded that the tuner that I have is not perfectly accurate, but it still is very close, with a standard deviation of 5.9%. And I also found that out of all the strings, the G string was most out of tune, even though that my tuner said it was perfectly tuned. Possible sources of error for my lab may have stemmed from human error, more specifically inconsistencies when I was recording my guitar notes. And a way to mitigate this in the future will be to have a more stable and reliable mic system, and to also ensure that each note is played exactly the same and at the same volume. Another possible source of error may have stemmed from the incorrect tuning of my guitar before the experiment. And a way to mitigate this problem in the future would be to ensure that my guitar is properly and accurately tuned to my tuner spec. Thank you for listening.